Hello and welcome to today's micro conference for the non-ferrous electrical sector. My name is Dane Armendariz and I am the technical advisor at the Wire Association International. I will be your moderator for today's program. This program is being recorded and will be available within a few days on the WAI archives and on YouTube. If you miss any part of the presentations or would like to forward it to another person, just check your email for an update on its release. It is my pleasure to introduce today's three presenters. Mike Prasad, who manages Gravure's California facility as Projects and Application Manager. He works in software design, communication, and implementation. Mike is here to help show you how to reduce print errors and increase productivity. Eric Xirinachs is General Manager, Deltacolor Masterbatch Division. He joined Tecnic in 2016, having completed his education in Spain and Germany. Eric kicked off his career in several industries. He held management positions at renowned industrial companies in Europe and Asia. Eric specializes in business-to-business industrial activities in technically complex environments, focusing on process efficiencies, enhanced quality outcomes, cost optimization, and constant improvement through technology innovation and new product development. And our third presenter will be Dr. Horace Pops, who is president of Horace Pops Consulting, a firm he founded to serve the wire and cable and metal sectors in 2005. He has dedicated his entire career to quality, production, and education through the wire sector. He is past president of the Wire Association and a frequent speaker at WAI events. He holds a PhD in metallurgy from the University of Pittsburgh, a master's degree in metallurgy from Lehigh University, and a bachelor's degree from Reslenor Polytech Institute. Let's begin with Mike and the Gravure presentation.
Here at GEM, it is our goal to help improve production for our customers and have been doing so since 1952. We were the first to introduce wire marking to the wire and cable industry through wheel printing. Oftentimes there are difficulties with printing on product. The difficulties come in the form of incorrect print legends that cost the wire and cable industry thousands, if not millions of dollars every year. Today, I'll talk about how connecting your continuous inkjet printing equipment to a control database through customized software can reduce or eliminate these harmful costs. The global wire and cable market was estimated at nearly $165 billion in 2018. If we consider the scrap rate of 2% that may have been caused by incorrect print errors, that equates to $3.3 billion in waste per year. Why is marking cable so important? I believe I'm preaching to the choir here when I say that wire cable marking is absolutely important for many different reasons. From import and exportation regulations to durability to being able to read the product identification, as well as ensure proper installation. It's also there for us to be able to brand, put your branding on the actual product itself, and obviously for safety and quality control. Scrap isn't the only problem that comes from improper marking. The rework that has to be done can be very costly and dangerous, depending on different chemicals used for rework. Incorrectly identifying a wire gauge can also be a very serious safety issue. Delivering incorrectly marked product to your client can create customer relation issues as far as trust. If your end customer cannot trust the fact that the product is properly identified, some of the ways that scrap is created is one of the most cable companies still employ operator entry as their primary mechanism to create their print. A few of the most common ways scrap is created is through human error, mistyping, incorrect spelling, or even incorrect legend selection. The operator selects the wrong print legend, a lack of standardization across different operating plants within a corporation. I've noticed in some cases, one plant decides to do it slightly different than another plant, as well as recalling incorrect data that's locally stored not up to date. You could have a local source of information that's not up to date with, say, the corporate headquarters, or marketing and sales might have more up-to-date information on what needs to be printed on the product, and that hasn't been completely relayed to the local operator, as well as if the counter information is correct, meaning it's printing every 2 feet or every 1 meter or every 1 foot. All of that information can lead to incorrect print errors. I would like to introduce an analogy here. If you consider to create a document and you went through and you spell checked it, you did a grammatical error check, as well as verifying that the content of that information was correct, and you now have to submit this report to your boss. So you then print out all of the information on your desktop printer, then you hand it to a colleague and then ask them to retype it as well as reprint it, and then send it along to your boss as your final report. We would question why. Why do we have to retype it? What sense does that make? It's a waste of time as well as a waste of resources. And there's also introduction of possibility of errors caused by the next person in line. The same way that you're questioning that process, that's possible that you're questioning that, it's the same way that we're currently doing, some companies are currently doing their work. They have information that's already been qualified, already been verified for accuracy, and yet we still print it out on a piece of paper and hand it to someone else to retype onto another computer, which is the printer, and then print on your final product. That leads us to why software integration is so important. It allows us to streamline that process so that we can create the messages locally, and we can make it as manual as we want it to be or as automated as we want it to be. Everything from being able to create and preview messages before they're even sent to the actual printer. We're also able to use stored data that's already been created. Keep in mind that what your operator sees as the final product of what needs to be printed on the product, on your actual wire, that information is already stored somewhere in your database. Someone had to tell that operator what needs to be put onto that product. Why not simply take that information and send it directly to the printer? That information is stored in different types of forms, like the databases that have unique identifiers that allow software to find exactly what needs to be printed. That's super important to understand. And as well as we have information that's already at our fingertips to allow us to print the correct product. We're able to then transmit data directly to the printer like you would your desktop, and you have different mediums to use. You can do it via local area network connection, or your network, or Wi-Fi, or even serial cable if you want to have it at a remote station. We also have the ability to take software and see if a out-of-the-box solution will work, or you can also customize software specifically for your application and your application needs. Keep in mind that we're in the year 2020. We walk around with processing power in the palm of our hands. There should be no reason why we can't simply take information that's already been qualified and certified and send it directly to the printer without introducing in more human error. We can not only send information directly to printers, we can also access different databases where this information is stored. Everything from SQL servers to Access to Excel, CSV, and even ERP systems such as SAP. The process goes, we connect to a database, then we modify the information into printable data so that the printer can understand, and then we send it directly to a specified printer And we can even make it so that as soon as a particular part number is selected from a particular PC on the production line, we can ensure that the printer connected to it is the one that will have the information sent to. Examples of databases, and this is just an example of a spreadsheet, just for presentation purposes, but you can imagine that your information is stored somewhere in your company where information, where some sort of identifier is associated with the information that needs to be printed. So example here would be the part number is 12345, and then the legend that you want printed on your product is something simple like, thanks for joining the webinar today. You also have some extra information like the unit of measurement. All of this is just an example of a wide variety of options that can be available for you to be able to print directly onto your product from your data source. So as an example here, the top line here, I pulled information from a specific cell within the spreadsheet, and the information printed there says, the information in the database can be in a particular format because data entry will be probably performed by sales or marketing or an authorized administrator. They're going to put information into that database in a format that's understood by people. So for instance, here, you understand that the product needs to print something like best cable in the industry, a UL logo, gem cable, a trademark, there's a 2-foot counter, and feet. Well, you don't necessarily want that exactly printed verbatim what's up there. You want it to be able to be converted into printable data that you can actually see on the product and it will actually make sense. We can use simple products like a find and replace. Software can then be used to convert the data from what you have in your database and then be able to populate a print string that will be understood by the printer, and then we can display as human readable code as you see in the example below. Now in the example below, it shows that the best cable in the industry and actually has a UL logo right there in the right spot, in the right place, and in the exact product logo that we want to print, gem cable, a trademark, again, placed in the right place, right spot, as it was in the original database, and then a sequential counter that has the data that's needed to print every 2 feet. It increments by 2, it has a certain number of values, and all of those are preset, or you're able, user defined. You're able to have these available and that can be selected and called out by information in your actual database. So what I'm trying to say here is that there are information in your database that was created by people and is able to be understood by the human eye, but maybe the printer doesn't understand, but we can convert that information into something that the printer can understand. And it should be this way. You should be able to use what you currently have. Some additional benefits to software solutions, in addition to what we've already discussed, are access to your production line from a local PC or from a central PC to allow you to see an overview of all of the production lines and the statuses of those printers on those particular production lines. The ability to remote into a specific printer to be able to do some minor troubleshooting for your maintenance staff, be able to access historical print data, as well as ability to log information for different events for future references. Convenience of creating a message at the PC rather than needing to spend time on the production line, as well as the ability to start and stop production remotely. In addition, you can also save time by not having to retype the message. So I guess in summary, you will increase productivity by reducing the amount of time that it takes to actually make a print string and actually print onto your product. You increase accuracy because the information has already been verified on your data source, and we simply translate it into information that the printer can understand, as well as you ensure safety for your end user because the product is correctly marked. And so by all of this, you're able to increase your productivity, and reduce all your print errors.
Well, thank you, Mike. That was very interesting. One of the things that got my attention was that 2% scrap number in dollars. That's a huge amount of money, and I think everybody would be interested in saving those kind of dollars. Which leads us to our first question, which sort of fits in with that. Question number one, I've heard software like this can be very expensive. How soon do you think our business would see a return on investment after implementing this software?
Well, keeping in mind that how much cost is involved in the scrap rate when you have incorrect print. I would imagine it's in the value of thousands of dollars. So your return on investment could be a year or less with or the amount of product that you're saving by not having to reprint, the amount of time, the liability, all of that is something that can be short term for return on investment.
Okay, next question. Are you familiar with the priority system? Can you deal with additional per production strings needed to be added to the base printing, such as date, batch, order, and so on?
A lot of these items can be prompted by the software so that you can have specific fields that can be populated prior to sending it to the actual printer. So you can bring up information that needs to be printed, and within the database, if there's a special area which requires operator to enter in some sort of value like batch number or employee ID number or something of that nature, all of that can be built into the software so that when the information is received, we can then prompt the operator to enter in the data that needs to be entered if that's what's necessary.
Okay, next question. For software, any interface is required for existing printers?
I'm not sure if I understand that question. Can you repeat it one more time?
Let's say for software, is any interface required for existing printers?
I'm not certain as to how to answer that question. You do not necessarily need an interface, but typically interfaces are necessary for previewing the print prior to sending to the printer. But the software, we can develop software as well as we have software that can be automated such that that the print is sent from your database directly to the printer, and then the operator is able to see the final product at any stage of the process. But you can make it automated so that it can go directly to the printer, and then you see the print on the actual product as your check, if that's what you want, or you can check the print along the process. So we can make it as manual or as automated as you want.
Next question, can you access this software from a mobile device?
We can develop apps to do so, yes.
How can the printer be networked into our existing system?
You have options of using, the printers are network capable. So you can assign IP addresses. We also have ways of using with extra hardware to enable Wi-Fi, and as well as there are Ethernet to serial adapters that allow for easy change out of printers without having to concern yourself with IP address changes, but assign an IP address to a converter which sits stationary with the production line, and then allows you to swap out printers without having to change the identification of that printer, but it'll be assigned to a specific production line. So networking is network drops or Wi-Fi or even serial.
So you having fun? We're just throwing all these questions at you like this? Okay. One last question. What kind of operating system is required for this software?
Windows XP or higher. Prefer Windows 7 or higher, but Windows XP or higher.
Okay. Well, Mike, thank you. You did a great job, and we appreciate your presentation. And I'm sure other people will be getting to you with more questions. Coming up right now is Eric Xirinachs. Eric, are you ready to go?
Okay, good morning. I would like to thank the WAI Association International for organizing this webinar and for inviting Deltacolor to speak. And thanks, Dane, for the introduction. So here I go. This presentation is about micro Masterbatches. They are intended to improve the dilution at cable extrusion processes. And I will structure the presentation in 7 parts. The first part are key values for a Masterbatch. So what is the value that a Masterbatch must provide? What is a Masterbatch good for? The second point is about dispersion. This is something that is 100% responsibility of the Masterbatch of the color concentrate manufacturer. Then I will briefly present different product sizes or pellet sizes that are designed specifically for the cable industry. The fourth point talks about dilution. I think this is the core of this presentation. It's a complex procedure with different factors playing a role, and it's critical for first-time quality, especially with high-speed cable production lines. Then I will go into dosing. That's also important in order to produce color regularity on the surface of cables. Then I will present 2 case studies. 2 case studies that we have done with 2 important cable manufacturers, global cable manufacturers, which have switched from standard pellet size to small pellet size and have gotten good results thanks to that change. And then I will finalize with conclusions. So let me go right into it. The values of a Masterbatch for the cable industry. It's 7 values. We have divided it in 7 values. The first one is dispersion, excellent dispersion of pigments. This is absolutely critical. This is 100% responsibility of the color concentrate manufacturer. It basically means that we have to divide pure pigment agglomerates into single crystal units, and I will show that later on with a video. The second point is to use as a carrier of the Masterbatch the same type of polymer as in the cable. This is quite simple. If you want to produce a PVC cable, you need the color concentrate carrier to be PVC2. If you produce a polyethylene cable, it must be a polyethylene based color Masterbatch, polypropylene, or fluoropolymers, or whatever polymer base you use. The Masterbatch should be produced with the same carrier. The third point is the selection of pigments. There are some pigments which may affect dielectric properties or may not provide the necessary light fastness, or may interfere with self-curing agents, etc. So it is critical that the pigments in the formulation of the Masterbatch don't interfere with what you want to achieve in terms of the performance of the cable. Critical point 2. Then number 4 is the selection of raw materials, so to ensure that the cable service life, the UV resistance of the cable, the fire resistance, the mechanical characteristics, contraction, spark test properties, etc., are not affected. Okay, so this is not only about the pigments in the formulation, it's also about the other ingredients. And this brings me to the 5th point. The ingredients must not interfere with the performance of the cable, with the features of the cable, but also these ingredients should not they should facilitate dilution. Dilution is a multi-factor phenomenon, if you like. There are several factors that play into why dilution is quick and effective. And And one of them is the formulation of the ingredients additionally to the pigments, the other ingredients in the Masterbatch, as well as other factors. I will explain that later also, and I have a video also that we will run that explains the different factors that play into dilution. Of course, the main message of today's presentation is that when you go down with the size of the pellet, you will have faster dilution. The melting process will be accelerated, and that will facilitate achieving homogeneous color, especially at high-speed production lines. Number 6 is the pellet regularity. This is often underestimated. It is critical to have pellet regularity. It provides several advantages. It provides easier dosing. It provides a possibility to go down with the quantity of Masterbatch used, so go down with cost. It also facilitates to increase of the production speed. So there are different benefits for the cable manufacturer when you have a regular pellet size and shape. It's not only about size, it's also about shape. And at the end, there is the point of the high pigment concentration. This is a critical point, I think. The higher the concentration of pigment inside a Masterbatch formulation, the more cost-effective the usage of that Masterbatch is, because at the end, the higher the portion of pigments in the formulation of the Masterbatch, the lower the dosage at the cable manufacturing process. Therefore, there is a clear saving in terms of quantity of Masterbatch purchased and used. There is an increase of cost, of course, of the Masterbatch itself, but the cost structure of a Masterbatch manufacturer works on several factors, and the quantity of pigments inside the formulation is just one factor. The production manufacturing costs are also in the cost structure of the Masterbatch manufacturing. Therefore, the increase of pigment concentration has a proportional impact on the reduction of the usage of Masterbatches in the cable extrusion process, but the increase of cost is not proportional, it's lower. Therefore, there is a saving on the side of the cable manufacturing. I will go back to that point later on. So let's go to the concept of dispersion. So as we can see in this video, when we purchase pure pigments, and those pure pigments are introduced into the production process, those pigments come in agglomerates, as we have seen in this picture. The first step of manufacturing is the mixing. The manufacturing, I'm describing now the manufacturing of the color Masterbatch, okay? In this mixing process, we start to separate those agglomerates somewhat, but the real work of dispersion happens at the extrusion process. So at the extrusion process, with these screws and hammers, we work mechanically on the material, and we separate those agglomerates into single crystal units, and we surround them by the corresponding polymeric base. And this is what we try to represent here with this 3D video. So we separate the single crystal units of the pure pigments, we surround them by the polymeric base, and once they are all, and this is what we call dispersion. And once they are all dispersed, then at the header of our twin screw extruder, we cut them and produce the pellets. And you can see at a microscopical level, you can see all those single crystal units of pure pigment dispersed and surrounded at microscopical level on the pellet, as you can see here inside the pellet. So this is what we call dispersion, right? So let's go back to the presentation. Here we go. So dispersion, to summarize, dispersion is the process by which the pigment agglomerates that usually appear with pure pigment powders, these agglomerates are mechanically separated into single crystal units and prevented from agglomerating again. And a well-dispersed Masterbatch provides improved first-time quality when used in the plastics transformation process. You get maximum color strength out of the Masterbatch when the Masterbatch is well dispersed. And again, this is something that is 100% a responsibility of the Masterbatch manufacturer. It is also critical for first-time quality because pigment agglomerate inside the insulation layer of, for instance, an automotive wire, at the end of the day is an impurity. It's an impurity that may lead to sparks and therefore may reduce first-time quality. So it's not only the color strength, it's not only the positive side, it's also the negative side. By providing perfect dispersion, on one side you avoid the negative side, you avoid sparks and impurities in the layer on the cable, and on the other side you increase the color strength that you obtain out of the Masterbatch. Let's go into the pellet types that are designed for the cable industry. On one side we have the standard pellet. The standard pellet on the left side. This one has a size of this is a cylindrical pellet shape, okay, and it has a size of 3 millimeters diameter and 3.5 millimeters length. Sorry for the metric system. Then we have the micro pellet. As you can see, the micro pellet is 3 times smaller in terms of diameter and more or less half as long as the standard pellet. And that means that it is several times smaller in terms of mass than the standard pellet, and therefore it melts much quicker, and therefore it facilitates dilution. The melting process gets accelerated. And this happens even more with the small micro pellet, which is only 1 millimeter of diameter, same as the micro pellet, but the length is just 1.5 millimeters, so it's much shorter in terms of the length. So these are the 3 products that are destined for the cable manufacturing. The first and the second, the standard pellet and the micro pellet, are to be used at the extrusion line, at the dosing unit at the extrusion line, and the small micro pellet may be used for those cable manufacturers who produce their own compounds at their compound mixing station. If we go to polyolefins, to polyethylene or EVA-based Masterbatches, we have 2 products that are destined to the cable industry. One is the standard pellet in polyolefins. This has a round shape, a spherical shape, because it's cut in water, and therefore by contraction due to the temperature change coming out of the extruder head, it contracts and it presents this spherical shape. That's a standard pellet. It has a diameter of between 2 and 3 millimeters, whereas the micro bead, that's what we call the small sized pellet for polyolefins, is just 1.5 millimeters big. Again, the smaller sized pellet melts quicker in the extrusion process, and therefore the dilution process gets accelerated. So going into the concept of dilution, which is a key concept, this is the process by which a Masterbatch is incorporated into the compound in the plastics transformation process. And here, again, it is critical. There are three things that play into this process, okay? We will run this video now, which explains the 3 factors that play, because one factor is the pellet size, the other factor is the compound used, and the other factor are the production parameters. So in this video, as you see now, in this first example, the size of the color pellets is quite similar to the size of the compound pellets. In some cases, when the size of the pellet is similar to the size of the compound, the color does not completely melt during the extrusion process. And here we see a simplification of a cable manufacturing process. You see here the extruder head, and here you see the layer on the cable manufacturer. You see the different laser control units, the cooling basin, and so forth, the spark test later on. But basically what we're explaining here is that if we go to faster extrusion lines, into faster cable manufacturing processes year after year, at a certain point, we don't have enough time for the color to melt and to incorporate homogeneously into the extrusion process, and therefore we produce a cable whose surface presents these lines, this non-homogeneous color, this color irregularity. Okay, and that's the problem. And sometimes that's the problem, not always. Sometimes with some colors, sometimes that's the problem, and I will go into that later with the case studies. Instead, if we go to smaller sized pellets, in this case with the microbead, you will see here in this 3D representation, you will see that the asymmetry between the color batches and the base compound batches is very big. It's a big asymmetry. Therefore, these much smaller pellets, they melt much quicker and therefore are able to produce a homogeneous surface, a homogeneous color surface on the cable. The process of dilution is the process of melting and incorporating the color into the compound, and that facilitates the regularity of the outer sheet, the color regularity of the outer sheet. Okay, so again, resuming, and I will go back to my screen. Basically, dilution is a game of three main factors. Okay, three main factors. One factor is the color concentrate itself, and what we say is that a smaller size pellet facilitates the melting and therefore the dilution process. The other one is the type of compound. Some compounds slow down the process of dilution and put a challenge in terms of the incorporation of the color in the extrusion process. And then, of course, there is the factor of the production parameters. So therefore, here it's a shared responsibility. In this case, the quality of dilution in the extrusion process is a shared responsibility between the color concentrate manufacturer, the base compound supplier, and the production parameters. Okay, and now let me explain a little bit about the dosage. The dosing depends very much on, because there's one doubt that some customers had when we go down with the size of the color master batch. And the doubt is the following: will these small pellets, will they decant, will they fall down during the dosage system? And this is something that is solved by what is called the mixing station or the mixing unit. In this case, we talk about plastic color dosage units from Voivod. You can see here on the left side the compound, on the right side the color pellets falling into the mixing unit. If you have such a mixing unit, what you achieve is a homogeneously distributed color master batch, and there is no such thing as the small pellets falling down and therefore posing a problem in terms of the dilution. And when this mixing unit discharges the material, as you can see here in the film, into the extruder, this homogeneously distributed pellets remain homogeneously distributed, and therefore, once they dilute in the extrusion process, you achieve a perfect color regularity, right? So this is what I mark here in this slide. I mark this mixing unit. That's the factor that guarantees that you don't get this other problem, which is the so-called decanting, the smaller pellets falling down and the bigger pellets remaining up, and then therefore they getting separated and therefore again facing some color regularity problems. Okay, let me go into the case study for PVC. So here, and it's very simple. Here we're talking about a global automotive wire manufacturer with factories all around the world, with headquarters somewhere in Europe, but playing all around, also in North America. And this customer had color regularity problems with 3 of 13 PVC based cables. And here we face the situation of some technicians having doubts about switching to smaller pellets because of the problem that I explained just before. However, we presented the smaller sized batches, the micro pellets in this case, and using this plastic color dosing system, which with this mixing unit that I just presented, avoiding this the effect of decanting to the pellet size difference. And what happened is that it went very well. Immediately, the customer got control over the color. The color finish changed and was regular. They didn't face anymore the problem with these lines, this color getting lighter and then darker as before, which in the case of the automotive wire, you may appreciate in the spool at the end. You have a spool, you have high-speed production, and then you have these color fluctuations. They go up and down, they get darker and then lighter, and then you can see it in the spool, and you may face non-conformities from the side of the customer. In all three cases, going down with the size of the pellet, they reached control over the color, and they could also increase the speed. So it's not only a question of improving the quality of the outcome of the product, it is also a question of productivity and cost at the end of the day, because they could go back to higher speed production, and also they could reduce the dosage. So they could reduce the quantity of color master batches used, because the normal reaction of the technicians at the production line when they have problems with the color regularity is to increase the dosage. They go up with the dosage in an attempt to compensate with this lack of color homogeneity, but it doesn't work. What does work is going down with the size of the pellet. Then the other case study, here we are talking about HFFR cable. You know, these flame retardant halogen-free systems at the compound, they pose also a challenge in terms of color. They sometimes put difficulties on the dilution process. And in this case, it was a big global player, a very big global player with over 100 factories worldwide, who is active in all kinds of cables: high voltage, submarine, telecom, energy, building wire, special cables, automotive, in all sectors. And in this case, we're talking about this HFFR cable with a green color, and they had these waves on the surface, these lines, this color irregularity. And we presented again the microbead in this case, because this was a polyethylene-based outer sheet with a smaller size. And again, the same results were reached. The customer could control the color and achieve perfect, homogeneous, regular surface. He also could go back to the more efficient extrusion speeds, and also they could reduce the quantity of Masterbatch used due to better control of the final color. So very nice results there with the small batches. Also in this case, we faced some doubts on the side of some technicians with regards to the asymmetry of the size of the pellet versus the size of the base compound, but again, it was solved easily once used with the proper dosage system. So these are the results that were obtained in these two case studies, which we're very happy about. And since then, several other cable manufacturers, especially in these two cases, in the case of flame retardant or halogen-free systems, those formulations normally are complicated and pose sometimes problems with color regularity. In those cases, going down in the size of the pellet solves the problem. And also in the case of high-speed cable production lines, like for automotive or for rolling stock or for building wire, in those cases, also going to smaller size pellets solves the problem. So resuming, going to the conclusions, new and shorter and faster extruders and smaller wall thicknesses of the insulation layer or of the outer sheet make it more difficult to obtain a perfect homogeneous color. And thanks to the smaller size, these new master batches are improving the quality outcomes in terms of color homogeneity. Using the smaller sized Masterbatches allows for an increase in cable production speed and an optimal finish, improving the productivity. Special polymer formulations improve the dilution process inside the extruder, helping to achieve optimum color homogeneity. This point is important. It's not only a question of the size. Size is critical. It's the main point, and it's the main message today. Smaller size melts quicker, therefore improves dilution, and you get a more homogeneous color. But the formulation of the Masterbatch is also critical. And at the end, elimination of overdosage, that is a critical factor in terms of efficiency and therefore of cost. You stop overdosing, okay? So that is the presentation, and let me put on the camera.
Eric, you did a great job. I really liked your videos and your case studies. They were very interesting and descriptive, and that was just super. Now, what I'd like to do is get to some of the questions that came in, because we have a few minutes yet. Okay, the first one is: are you familiar with an influence of a specific color on the electrical data performance? For example, all colors work except the green.
Yes, it sometimes happens, especially the phthalo, the so-called phthalo greens, pose problems. It's about the choice of the pigments. The interference, it is incredible how many kinds of interference can happen between certain pigments depending on where they come from. This can happen both with organic as well as with inorganic pigments. Depends on where they come from, how they have been produced, and it depends also on what performance you want from the cable. And electrical interference is one point, and there are many others. The only way to find out is testing. So what we always suggest in those cases is explain the problem. Let's test in the laboratory and find out which formulation will pose no interference. And then we formulate according to those findings. And then it's critical to guarantee that once this formulation has been approved technically for this application at the customer, that the formulation remains. That's critical. And this is not only a question of the color Masterbatch manufacturer, it's also a question of the compound supplier. You have to stick with the formulations and not change them, especially not changing them without informing the customer. But absolutely, yes, that's correct.
Good. The next question is Delta dedicated exclusively to the cable industry?
Mainly, yes. Delta Technic, since its foundation in the early 80s, has chosen just two industries. One is the cable industry, which is now about 65–70% of the total activity of the company, and the other one is PVC products. Like profiles and pipes and PVC compounds. Most of the PVC goes back into the cable industry because PVC is still a material that has many electrical and mechanical advantages, and it's also cost effective. So for instance, in the automotive industry, more than 50% of automotive wires are still PVC based. But yes, Delta Technic is focused on the cable industry. And not only on that, Delta Technic is very much focused on what happens at the extruder line, at the cable extruder line. So we try to understand the specificities and challenges at the extrusion line, not only for automotive wire, also for energy cables, also for telecom cables. And we try to solve them through the color Masterbatch. Sometimes some problems can be solved through the color Masterbatch. So this is the specialty of Delta Technic, in fact.
Good. Next question, is there a price difference between a small micro pellet and a normal pellet?
I was fearing this question would come, and here it is. Yes, there is, but, and this but is important. The difference between the standard pellet and the smaller pellet, and the smaller pellet is a little bit more expensive to produce. Keep in mind, this is because of industrial reasons. We have an extrusion line also, as you have seen in the first video. And when the extruder head with the little holes where the pellets come out has a smaller size, it forces us to go down a little bit with the production speed. And therefore, our production efficiency goes down a little bit, and therefore the cost goes up a little bit. It's a very small difference. It's a very small price difference between the standard pellet and the micro pellet. It's a small price difference. And in those case studies and with many other customers, the bottom line has been beneficial in terms of cost for the customer. So the reduction of dosage, the increase of first-time quality, and the increase of production speed, all those factors largely outweigh the difference in price. But at the end, this is for the cable manufacturer to find out and to decide at the end of the day.
Great. Next question. Does Delta have production in North America?
Almost. This is first-hand news because we have not yet made any press release, but as we have announced this already on our LinkedIn portal, I can also say it here, and I'm happy to say that we are progressing well with the building of our factory. It's not in the US, it's in Mexico, but Mexico is within the USMCA, so we understand this is part of North America. It was called NAFTA, and the N of NAFTA means North American Free Trade Agreement, so therefore we understand it's North America, and it's above equator anyways. So yes, we have a factory. We have a factory in Mexico, which is under construction. It will be ready before end of this year. We expect to do industrial tests by November, December this year, and it will be fully operational at the beginning of next year. Also, we are building a sales office in the United States, and we will inform you about that in the following months.
Super. Now, a few other questions did come in, which we will send to Eric, and he can get back to you with answers and follow up. But Eric, we want to thank you for an excellent presentation, and look forward to hearing from you in the future.
Thanks for having me.
And with that, you're welcome. And with that, we're going to be moving on to Dr. Horace Pops for his presentation, and give you a minute to make the changes. It looks like he's here. That's great. Dr. Pops and I have two things in common. We both are University of Pittsburgh graduates. Of course, his degree is much higher than mine is. And also, we're both Steeler fans. And I'm watching now to see if half of the attendance fell off. No, they didn't. That's good. Okay, with that, I'll turn it over to Dr. Pops.
Okay. First, I'd like to give some acknowledgement to the Wire Association staff for doing such an excellent job of preparing all this.
The pictures I'm going to show were all taken on copper wire. However, it doesn't make any difference whether material is ferrous or non-ferrous. The wire breaks are the same. The most important part of a wire break analysis is to distinguish between problems that are caused by the incoming material or by the wire drawing process itself. My recommendation is that somebody in quality in the plant look at all the wire breaks. The operators don't have time. They need to collect the wire breaks, but I recommend that pictures of all the common kind of wire breaks be posted somewhere near the wire drawing machines so the operators can have a good feel as to what the cause of the problem might be. So material versus processing defects is one of the first four things I want to talk about. Unfortunately, there are so many different types of problems, either in the material or in the wire drawing process itself, that it would take probably over an hour to go into all of them. So again, the most important thing is to know which category the breaks actually fall. For identification, how do you know what's going on? Well, the most important thing is having a stereo microscope. A standard stereo microscope will be able to look at all the wire breaks and wires being drawn, unless they're actually ultra fine, extremely fine, maybe finer than about 52 AWG. So that's, what most people can do. As far as elemental analysis, that's when you have an inclusion. There is equipment that does it. Most wire plants do not have it, but almost all commercial laboratories can. So all you need to do is send them the inclusion, and they can do an EDAX or elemental analysis, and it'll tell you what's going on. Metallography is examination of the rod or wire by making a cross-section. And again, this is used primarily to find out the exact cause of the break in more detail. So here we go. This is a copy of the wire that's got a very poor surface. And this is usually caused by fines that are present in a wire during the wire drawing process. Here's a wire break. And again, there are some surface defects near the break. This was probably caused by fines inside the drawing die, so that there was very poor lubrication, leading to a high force on the wire, and a resulting wire break took place. Here's another example of some surface defects on a wire being drawn. They look different. This is caused by poor lubricity, poor lubrication between the die and the wire being drawn. This was on the rod with a crack, and if you look at a cross section of it in this picture, now you can see that the crack is very irregular, and that's because it took place at elevated temperatures at the grain boundaries, and since it was hot, it was exposed to the air and oxidation took place. So this is now probably a wire break that was caused during casting, during solidification, in the process of making the casting bar. Here's another example on the left. You can see a crack in the rod. And if you look at the right picture, you can see that there's a crack, but it looks completely different. And near the surface, there's some gray material. Well, that happens to be slag that got carried over from the molten metal into the cast bar, was on the surface, and that's what caused the crack that you see on the right. Here's another cross-section of a rod, and this looks different. This was caused by the corners of the cast bar getting folded over during the hot rolling process. So once again, a lot of the defects can occur even before the wire drawing process takes place, but during the preparation of the rod. Here's a cross-section of a copper wire that was etched to show the grain boundaries. And as you can see near the crack, there are some very large grains. What you're looking at is a duplex grain structure that was caused by some heating of the rod. That took place during the hot welding of the rod. So this happens to be what you would call a weld break that was caused by the improper conditions during the welding process. Now, the break doesn't always occur in a rod. You might be able to draw 5, 6, even 10 dies down and subsequently get a wire break. And so the only way to tell would be to do something like this. Polish it, etch it, and see if you're seeing any subsurface duplex grains that are present. Here's an example of an inclusion. The inclusion on the right is small enough so it hasn't caused the break. Once again, if the inclusion is too small, you may not get a break until it's a smaller size wire. And in general, when the inclusion reaches approximately 25 to 30% of the cross-sectional area, then you'll get a wire break. In the picture on the left, that's a wire that's just about ready to form a wire break. You can see the inclusion and there are cracks surrounding it. Sometimes the inclusion actually falls out when it breaks and is not present. If it is present, there's only a 50-50 chance it'll be left in the end of the wire that's left in the wire drawing machine. So because of that, because of the absence of inclusions, probably 85% of the time, if it's an inclusion-related break, you don't know what the origin, and you can't tell what the actual mechanism was at the beginning. Here's an example of a ferrous inclusion, just like I was talking about. And on the right is an example of what the EDAX print light show. And it gives you the elements that are present. And from that, it can tell you what actually is that inclusion. And as I say, most of the ferrous inclusions are H13 tool steels that are used for the hot rolling process. Here's another example of a copper wire, but in this case, there's a whole bunch of inclusions. They're all magnetic, and it turns out this happens when a piece of steel accidentally got embedded in the molten metal being cast, and it broke up. It usually isn't there that long, so it doesn't dissolve completely, but it breaks up and gets involved into the cast bar and into the surface of the rod and into the wire. And this could be caused by something like an operator accidentally losing a tool and it falling into the molten bath. Now, I want to talk about a subject called central bursting. I don't know what you call it. Some people call it central bursting. Some people call it hollow wire or cuppy wire. But usually there are both cups and cones present. This is an example now of what a brittle cup and cone break looks like. The sample on the left has a hole in it, so that would be called the cup end. The sample on the right fits there, and you can see that would be the cone end going into it. That means if you had both ends of the break, each end would look different. Now, here I'm showing cuppy wire, and if it takes place in a rod breakdown machine, then the cone end points in a direction of wire drawing, and the cup end is the opposite end. So if it's cuppy wire in a rod breakdown machine, you would have in the machine the cone end, and the cup end would be lost. Now, central bursting is usually caused by poor die geometry. That means too small a reduction in area, okay, or too large a die angle. But look at the corrections. Improved lubricity, that's a drawing related issue. Well, replace a worn die makes sense. If it's worn too much, you might be getting a smaller reduction in area. Sounder casting, that's interesting. That means a defect in the cast bar or in the rod could exacerbate this particular problem. Smaller die angle, well, that's what I said. If you have too large a die angle, you have stresses inside the wire, and it can cause a crack or improve the drawing practice. Well, let's see how all that comes together. Some years ago, people made some calculations, and they found that cuppy wire is caused by two things. As I said, too large a die angle or too small a reduction in area. Now, the green zone would be sometimes with a certain amount of wire drawing history, so to speak. So the yellow end would be a case when you've got good friction and things going well. Generally speaking, no matter what you're drawing, the point that you are is in the safe zone or above the yellow curve. But now if lubrication takes place and you got very high coefficient of lubrication, you're below the green curve, and therefore central bursting is likely to take place. This is a cross-section of a wire inside the wire, so you wouldn't see this with the naked eye. But you can see this is the beginning of central bursting taking place. There's a void, that black area is the void, and you can see a cone starting to form. Actually, a crack is forming on a 45-degree plane. So a 45-degree plane in 3 dimensions would be the surface of a cone. But what caused it initially was where it began. And very often, as I said, this takes place in the exact center of the wire where the tensile stresses are the greatest. So here's an example now of a cone taking place. But inside, there's a little void. There was some macro porosity, which exacerbated and caused this cuppy end of the wire break to take place. This happens to be a curve only for copper. It shows that the amount of wire breaks increases as the oxygen content gets too high. Oxygen is not the cause of the problem, but it means with higher oxygen content, it makes the wire less ductile, more brittle, and cracks are more easily likely to form and to propagate more easily. So again, it's not the cause, but it makes the wire break occur much more easily. Now here's a cross-section, longitudinal cross-section of a wire. There's a wire break at the end, and you can see that there's some void that is sort of present. But look now down over here. Here you can see a cone end pointing in a direction of wire. But here now you can see the cone end pointing in the opposite direction. This is taking place in both directions, and it's not uncommon. So we have to be able to explain why this particular process takes place. So let's start over here schematically. Let's say in a rod breakdown machine, and something is wrong with the die, okay? Die angle, reduction in area, and a crack forms. And the crack will continue to grow, get bigger and bigger. And maybe if it occurred late in the process, you will get a wire break in a rod breakdown machine, and the cone end would be pointing in the direction of wire drawing. Now, supposing this is the process wire as it exited the rod breakdown machine. You can see it hasn't broke, but there's a defect in it. Now, what happens in a wire rod breakdown machine? When you take that process wire and put it into the secondary machine, it's going to be drawn in the opposite direction. So this is now what that wire would look like in the secondary machine. There's a crack here, but it's going to increase as you draw it down. And if it breaks in the secondary machine, you'll have a cup end point in a direction of wire drawing. So it would be different than what took place if it happened in a rod breakdown machine. Now, supposing once again that this is the wire going into the secondary machine and you start to draw it down. Now, supposing you got drawing problems in your secondary machine, then a crack may form. It's starting to form in a drawing direction. And in this particular case, you'll have cones pointing in opposite directions. And that's exactly like that picture that I showed just previously. Lookalikes. Well, this turns out to be a sample. These are both ends of the break, and there's a hole in the middle of both samples. There's a little bit of ductility, so slight reduction over here. And this is caused by a casting problem in the rod called macro porosity. That always usually occurs anyway in the last portion of the metal for solidification to take place. So it's almost always in the center of the cast bar. If it's too big and doesn't get eliminated during hot rolling or wire drawing, there'll still be a void that's present, and it will cause that wire break. So again, this is a casting-related issue. Now, here's what I showed earlier. This end of the break over here, the cup end, does look very, very much like this over here, okay? But they're caused by different things, and it's so easy to get them mixed up. Generally speaking, if you are looking at the break, see if there's a 45-degree shear over here, which is indication of a cup end. Because of the difference, I always recommend, even if it's banged up, if you're collecting wire breaks, to collect both ends, both the wire break that's in a machine and the end of the wire break that went through and maybe it was all banged up. Because this end, even if it's deformed, would look different than this end to show it's a cuppy wire break. This happens to be a tensile break, and there's a void. Tensile breaks usually occur in ductile materials. These voids are not the cause of the break, but they usually occur as a result of wire necking down and forming a tensile type break. Now, here's an example of a cone end of a brittle cup and cone break. Here's another sample. it looks very similar, except you can see something over here. This looks like it might be something sticking in. This is the reason why I recommend that if you do get a break, you try and clean the wire with an ultrasonic cleaner to remove any residual drawing lubricant that might be present in a particular wire break. So here now you can see something else. Here there's an inclusion, and it's present inside what looked like some macro porosity break. If you make a cross section of that wire, you can see it's the original same structure, same copper that was being drawn, but this is the as-cast structure. So this particular inclusion fell into the melt, it went into the center, and during wire drawing, because it wasn't compressed as much during drawing, you can see some of the original shape of what that inclusion was.
Well, thank you, Horace. I mean, that was great. I enjoyed all the slides. It was very descriptive. We have a few questions here. The first one is, are the inclusions introduced in the annealing process?
Usually not. What usually happens in the annealing process, you may get some contamination inside the annealer furnace, and you may get some oxidation or something, but usually you don't get inclusions in annealing furnace. Yeah, you got to be careful though. Sometimes a furnace might have an inclusion, a refractory problem. And if refractory falls from the inside of the furnace, it might fall onto the copper being drawn, and then it would be an inclusion present taking place. But the only way to tell would be to do an EDAX, and it would show it's probably some of the organic material that's used in a refractory, silicon or something like that.
Does oxygen content increase during annealing the rod?
Only if you have some kind of a leak in the furnace. Generally speaking, people say that if you have more than 100 ppm of oxygen in the annealing furnace, you'll get oxidation taking place. So that's where that might take place if you've got a leak in the furnace. And usually it's oxidized just at a few selective locations near where that problem was in the furnace. It's not that common, but it definitely can take place.
Great. Okay, next question. Any break originate due to rolled in oxide?
Into what kind of oxides?
Rolled in.
Rolled in.
Would a break?
Well,
yeah. Would a break originate
rolled
from
in
rolled
break.
in oxide?
Yeah. Usually, the rolled in oxide is at the surface of the rod, and it's either not pickled properly or it's not mechanically descaled properly. That's the reason why in the production of copper, you have to determine the surface oxide thickness at the uniform surface oxide thickness. What happens is occasionally a little particle of the scale gets removed, but it gets embedded back in the trailing end of the rod and the rolling mill, and that definitely will cause oxide-related problems and probably a wire break. And it may not even show up in the surface oxide test if you don't have that particular location where you're testing. So I'd have to say that oxides, because of poor removal in the rolling mill, are the single largest case of oxides taking place in the rod.
Thank you. Next question. What is the source of crow's feet on the wire surface?
Well, it can be a number of things. As I said, it's poor lubrication. So what happens is the wire being drawn doesn't have a lubricant between itself and a die. So therefore, the copper or whatever material you're drawing adheres or sticks to the die. Therefore, the material being drawn is rubbing against itself rather than the diamond or polycrystalline material. And therefore, you've got very, very high friction, and therefore you will get both fines being formed and possibly wire breaks taking place. And what is wrong with, what's the origin? It's hard to say. The temperature of the lubricant could be off, too high, or not during the temperature range that's recommended by the lubricant supplier. It may need some additives, so you got to periodically check the composition of the lubricant to see if anything is getting out of hand. And if it looks like you have to make additions too quickly, then you know something is wrong and it might be time to replace the solution. So I'd have to say those are the biggest problems why you have poor lubrication between the material and the die, just not contact with the die being used for the drawing operation.
Okay. Next question. How about water-based annealing? Does it lead to oxidation?
Usually not. Usually the water comes off and doesn't usually lead to oxidation. I should point out, though, that if you don't remove the drawing lubricant very well, it's possible that the drawing lubricant may react with the wire being drawn and form some organic compounds, and that would be seen, that would be present in the wire breaks. I do recommend that you periodically look at these wire breaks and the fines being formed, because that might be an indication as to what the problem is, especially the fines, which will be related to somewhat of the abrasion between the die and the wire being drawn. It'll also tell you if there are slivers taking place or anything else, organic materials, etc., if you look at the fines that you have in the drawing machine.
Okay, one last question. Which type of protective atmosphere is better, nitrogen or steam?
Well, they're both capable of doing the jobs. Steam is usually used. I guess it's a matter of cost, what's better. But in both cases, you got to make sure that it's being applied properly.
Great. Well, thank you very much, Dr. Pops. In closing, I want to thank today's panelists for your insight and for your time today and all the work you did in putting together these presentations. If there's any questions we didn't get to, they'll be sent to the presenters so they can answer them individually. In closing, I want to thank everybody for joining us on this Wire Association International's webinar. Just want to remind everyone the Wire Association, for its first ever streamcast, will be on July 15th. The live broadcast includes 10 sessions featuring a combination of presenters, subject matter experts, and guest speakers. And with that, this brings the WAI's presentation to an end, and thank you again for attending.